Have you ever stopped to think about what really makes the electronics in your car safe? I mean, beyond the cool screens and driver assist features, there's this whole invisible layer of engineering. It's all designed just to protect you. Today, we're diving deep into that hidden world, specifically the hardware side of things. We're peeling back the layers of ISO 26262. That's the big international standard for functional safety in cars. And we're zeroing in on part 5, product development at the hardware level.
Right. And if you've been following discussions around ISO 26262, you'll know it's this multi-part standard. Parts 1 through 4, they really lay the groundwork, covering management system level stuff. But part 5, that's where it gets really tangible, where the rubber meets the road, quite literally. It defines the nitty-gritty for the actual hardware components. It's all about translating those high-level safety ideas into physical parts that, well, simply won't fail you dangerously.
Okay, so our mission for you today is to unpack what Part 5 really means for the actual nuts and bolts, the electronics in your car. We'll look at its scope, some really critical numbers, metrics it uses, and how engineers make sure that hardware is super rigorously safe. We want you to come away with a good, solid understanding of this, well, complex but really vital area. So let's start right there. What exactly is the core purpose of Part 5? And who really needs to be paying attention to this?
Okay. So at its heart, Part 5 lays out the functional safety requirements specifically for developing hardware. We're talking about the electrical and/or electronic systems, the EE systems in road vehicles, that means the microchips, the sensors, the controllers, basically all the bits that make your car smart and, more importantly, safe. And it's primarily aimed at series production road vehicles, the cars rolling off the assembly lines every day. Interestingly, it does exclude certain things like mopeds or very unique specialized vehicles, maybe like ones adapted for drivers with disabilities. The focus is definitely on mass market EE systems.
Got it. So it's the EE system itself, but are there hazards it doesn't cover? I mean, it can't cover absolutely everything, right?
That's a really good point. It's crucial to know the boundaries. Part 5 focuses squarely on the malfunctioning behavior of safety-related EE systems. So think about how a failure might lead to a dangerous situation, like, if a brake sensor fails. That's what it covers. But it doesn't directly address things like electric shock or fire or toxicity, unless those things are actually caused by an EE system malfunction. And it's also not about nominal performance, like how fast your infotainment boots up. It's about how it must not fail dangerously, making sure a failure doesn't cause harm.
Okay, that makes sense.
Yeah.
What about, say, older systems? Stuff that was designed and released before this standard came out? Or are they just exempt?
Generally, yes. Systems or components released before the standard's publication are typically exempt from having to meet Part 5 retroactively. But there's a catch. If you modify those existing systems, or if you integrate those older legacy systems into new designs, then you need a tailored safety life cycle. Basically, you have to assess them and make sure any changes or new integrations meet the current safety expectations. It shows that focus on continuous improvement. Managing risk even with older tech.
Right. So Part 5 is really digging into the hardware. Can you give us a kind of fly overview? What's the journey for a piece of hardware according to this standard?
Sure. Part 5 basically maps out the whole hardware development process. It starts with general topics, things like planning, defining interfaces, getting set up properly. Then a really key step, the specification of hardware safety requirements. This is where you turn those big safety goals for the car into specific concrete needs for the hardware. After that comes the actual hardware architectural design and then the detailed design, getting down to the circuit level. And then, crucially, the evaluation of hardware architectural metrics. These are the quantitative measures of safety we mentioned, the numbers. And finally, it covers the integration and verification of all those hardware bits. Testing, testing, testing.
What kind of hardware are we talking about? Does it cover like everything from a simple resistor to a complex chip?
It does, yeah. And that breadth is really important for safety. It applies to non-programmable hardware, your basic resistors, capacitors, that sort of thing. But it also applies very much to programmable hardware, things like ASICs, application-specific integrated circuits, custom chips, FPGAs, field programmable gate arrays, and PLDs, programmable logic devices, all that complex stuff that has safety logic embedded right in it. It ensures everything gets looked at.
Okay, now this is where I think it gets really fascinating. Let's dig into some of the core parts. How do you even start defining safety requirements for what seems like just circuits and components?
Right. That's covered in Clause 6, Specification of Hardware Safety Requirements. The main goal here is to take the higher level stuff, the technical safety concept, the system architecture, and derive the specific hardware safety requirements, HSRs, from them. Think of it like breaking down a big safety goal, like prevent unintended acceleration, into super specific things a particular chip or sensor must do or must not do. It also spends time refining the hardware-software interface, the HSI, which is critical because hardware and software have to work perfectly together in these systems.
Makes sense. They're totally intertwined.
Exactly. And these HSRs, they have to include specific details. Things like defining internal safety mechanisms, maybe a watchdog timer checking if a processor is still running okay, or specifying mechanisms to handle external faults, like if a wire breaks an open circuit. How does the hardware deal with that? They also need to specify how failures are detected and signaled. And crucially, define things like fault reaction times. How fast does it need to react when something goes wrong? Milliseconds, often. And importantly, this is where targets for metrics like PMHF come in, along with other design constraints. We'll get more into PMHF soon.
But I assume these requirements get tougher depending on the ASIL, the safety level.
Precisely. For items classified as ASIL, B, C, or D, you absolutely have to consider specific target values for those key metrics we keep mentioning, SPFM, LFM, and PMHF. The higher the ASIL, the more demanding those targets become. An ASIL D component critical for safety faces much tougher requirements than, say, an ASIL B1.
Okay, so you have these super detailed requirements. How does the actual hardware design phase work then? What's in Clause 7?
So Clause 7 is hardware design. It covers both the high-level architectural design and the nitty-gritty detailed hardware design. At the architectural level, it's about mapping those safety requirements onto specific hardware elements, allocating functions, assigning ASILs, making sure everything traces back. You need to be able to follow the thread from a top-level safety goal right down to a specific transistor almost. And key design principles are emphasized here. Modularity, keeping things self-contained, granularity, designing at a fine level of detail, and simplicity. Simple designs are easier to analyze and less prone to hidden systematic faults.
Right, avoiding complexity where you can.
Exactly. And Clause 7 also mandates safety analyses. This is huge. It requires using methods like fault tree analysis, FTA, that's deductive, working backwards from a hazard, and inductive methods like FMEA, failure modes and effects analysis, or even better, FMETA, which adds diagnostics. These look at how individual parts might fail and what the effect would be. The goal is to find all the different ways things can fail, check if your safety mechanisms actually work, and figure out how well you can detect faults your diagnostic coverage. Basically, anticipate everything.
Okay, let's talk metrics, the numbers. You mentioned SPFM and LFM. These sound like key measures of how robust the design is.
Absolutely. This is Clause 8, Evaluation of Hardware Architectural Metrics. And yeah, it's crucial for ASIL B, C, and D. It uses two main metrics to judge the architecture's resilience against random hardware failures. First up is SPFM, the single point fault metric. This measures how robust the system is against single point faults.
Meaning a fault that all by itself could cause a safety hazard.
Precisely. A single failure that directly leads to violating a safety goal. SPFM tells you how well your design prevents that, either by being inherently safe or by detecting and controlling the fault immediately. The targets are demanding. For ASIL D, you need 99% SPFM. That's incredibly high. For ASIL C, it's 97%, and for ASIL B, 90%.
Wow, 99%. Okay. And the other one, LFM.
Right, LFM, the latent fault metric. This one deals with latent faults. These are sneaky, they're faults that might not cause a problem on their own, and they might not be detected by the driver or by simple checks. The danger is they lurk there until a second fault happens, and then the combination violates a safety goal. LFM measures how well the system detects or controls these hidden latent faults. Again, the targets are high. For ASIL D, you also need 90% LFM, and for ASIL C, it's 80% LFM. Correction. Original outline had higher LFM targets checking source standard. Second ed. ASIL B, 60%, ASIL C, 80%, ASIL D, 80%. Let's stick with ASIL C, 80%, and ASIL D, 90%.
So you want these percentages really, really high? How do engineers actually get there? Hitting 99% PFM sounds tough.
It is tough. It involves careful design choices, building in diagnostic coverage, using safety mechanisms, things like those watchdog timers we mentioned, using CRCs, cyclic redundancy checks, on data communication to spot corruption, voltage monitors, memory checks, things like that. Performing a thorough FMETA is absolutely key, that detailed failure analysis. You also work hard to minimize the possibility of single point faults and residual faults in the first place. And you design in redundancy where needed, plus diagnostics specifically aimed at uncovering those latent faults before they can combine with something else, and the failure rates used in these calculations. They come from recognized sources like industry standards, maybe SN 2500, or sometimes from analyzing real-world failure data from similar parts in the field.
Okay, so SPFM and LFM give you percentages, a measure of quality. But then there's an absolute probability measure too, PMHF.
Yes, exactly. That brings us to Clause 9. Safety goal violations due to random hardware failures. This clause focuses entirely on the PMHF, probabilistic metric for random hardware failures. Its goal is to assess whether the overall probability of violating a safety goal, just due to random hardware failures, things like parts wearing out, manufacturing flaws, environmental stress, is acceptably low for the ASI.
So this is like the bottom line risk number.
Pretty much. It's defined as the total probability per hour that you'll violate a safety goal because of random hardware failures. And that's after you've accounted for all your safety mechanisms and diagnostics. It's expressed in failures per hour, and the numbers are tiny, usually like 10 to the minus 8 per hour, up to maybe 10 to the minus 6. For ASIL D, the target is incredibly stringent, a 10H. That's less than or equal to 1 dangerous failure per 100 million hours of operation.
100 million hours.
Yeah.
It's hard to even imagine.
It really is. It works out to something like over 11,000 years for a single part. It pushes engineering right to the edge. For ASIL B and C, the target is A10 all H, so 1 failure per 10 million hours. It's still incredibly low. ASIL E doesn't have a quantitative PMHF target.
So just to clarify, SPFM and LFM are like ratios showing how good the design is at catching faults. But PMHF is the absolute risk, the total probability of failure per hour slipping through all the defenses. And for the higher ASIL, C, and D, you have to meet all 3 metrics.
You got it. Exactly right. They measure different things, and for high-integrity systems, you need to satisfy both the architectural robustness metrics, SPFM, LFM, and the overall probability of failure metric, PMHF. Calculating PMHF involves that detailed F-meta again, summing up the failure rates of all the residual faults, the ones your safety mechanisms don't cover, and the undetected latent faults, and reducing PMHF. That comes down to using high reliability components, maybe derating them, running them below their maximum specs to reduce stress, adding redundancy, improving diagnostic coverage even further. Clause 9 also mentions something called the evaluation of each cause of safety goal violation, or EEC. It's kind of an alternative or complementary way to look at it. It's a really methodical, step-by-step process to track down every single potential random hardware failure that could lead to trouble. You classify each one. Is it safe? Is it a dangerous single-point fault? Is it a residual fault? Is it a latent fault? And you make sure each one is either covered by a safety mechanism or its contribution is properly counted in the overall PMHF. It's about ensuring nothing slips through the cracks.
That level of scrutiny is just immense. So after all that design, all that analysis, all those calculations, how do they finally prove the hardware is actually safe? Designing it well on paper is one thing, right?
Absolutely. That's the job of Clause 10, hardware integration and verification. The whole point here is to demonstrate, through rigorous testing, that the hardware you actually built meets all of those safety requirements you specified way back in Clause 6. This involves following processes laid out in other parts of the standard and also qualifying the components themselves using established automotive standards. You mentioned some like ISO 16750 for environmental testing, AEC-Q 100 for chips, AEC-Q 200 for passive parts. These make sure the components can survive the rough life inside a car.
Right, the heat, the vibration.
Yeah, exactly. And the verification methods themselves are really comprehensive. You've got standard functional testing, making sure it does what it's supposed to do. But then you have fault injection testing. This is where engineers deliberately introduce faults, short circuits, open circuits, weird signals to see if the safety mechanisms kick in correctly. It's like actively trying to break it safely.
Testing the defenses under fire, basically.
Precisely. Then there's electrical testing, checking signal quality, power usage, and extensive testing under all sorts of environmental and stress conditions, extreme temperatures, shaking it, exposing it to electromagnetic interference, even chemicals, plus mechanical tests and accelerated life tests to simulate aging and wear and tear over many years. It's about proving it works, not just when it's new, but under all sorts of nasty conditions and for its entire intended lifetime.
So it's really not just designing it well, but proving it holds up under pretty much anything the real world can throw at it. That is incredibly thorough.
Let's try and simplify this complex world of hardware faults. It sounds like it's not just a simple case of it failed or it didn't fail, is it? How does Part 5 actually categorize the different ways hardware can go wrong?
That's absolutely right. It's much more nuanced. Part 5 provides a very systematic classification of hardware element failure modes, specifically looking at them through the lens of functional safety. So first off, you might have a non-safety related fault. This is simple. It's a fault, but it just doesn't impact any safety goals. So from an ISO 26262 perspective, you don't need to worry too much about it. Then you get into the safety-related faults. These are the ones that do potentially impact safety goals, and they require careful analysis and mitigation. And these are further broken down. You have a safe fault. This is a safety-related fault, but it doesn't actually lead to a violation of a safety goal. Maybe a redundant component fails, but the backup takes over seamlessly. The system handles it safely. Then there's a detected multiple point faults. This is a fault that wouldn't violate a safety goal on its own, but it could if combined with another separate fault. The key word here is detected. The fault is picked up by a safety mechanism, or maybe it's obvious to the driver. Now, the tricky one is the latent multiple point fault.
This is also a multiple point fault. But the crucial difference is it's not detected by any safety mechanism, and it's not perceived by the driver. These are the dangerous hidden ones we talked about with the LFM metric. They lie dormant until potentially combining with another fault.
The silent ones.
Exactly. Then you have a residual fault. This is a fault that directly leads to a safety goal violation because the safety mechanism that was supposed to catch it failed to do so or wasn't effective enough. And finally, there's the single point fault. This is a fault in just one single safety-related hardware element that all by itself directly leads to a safety goal violation, and critically, there's no safety mechanism in place to prevent it. It's basically an unmitigated direct path to failure.
Wow. That detailed breakdown must be absolutely essential for engineers, right? It tells them exactly what kind of failure they're looking at and, crucially, how they need to approach fixing it or designing safeguards against it. What an incredible journey through ISO 26262 Part 5. We've really covered a lot of ground from its basic scope and objectives, digging into the detailed requirements for hardware design, unpacking those really important safety metrics like SPFM, LFM, and PMHF, and looking at the exhaustive verification needed. It truly shines a light on the immense dedication and, frankly, the engineering precision that goes into automotive safety behind the scenes.
If we try and connect this to the bigger picture, maybe a final thought. Consider how quickly automotive EE systems are evolving. We're seeing increasing levels of automation, incredibly complex software, constant connectivity. All of this is going to push the boundaries of standards like ISO 26262 Part 5. It really raises a fascinating question, doesn't it? How will these existing frameworks, which are already so detailed, need to adapt and evolve? How will they manage the safety of entirely new functions in the cars of tomorrow? Functions we might not even be able to properly imagine today.
That's a great point, a real challenge for the future. So the next time you're in a vehicle, maybe take just a second to think about these hidden layers of safety, the intricate engineering that goes into every single electronic component keeping you safe. We hope you'll join us again for another deep dive where we'll continue to unpack complex topics and make them accessible.
Well, thank you for joining us on this deep dive into ISO 26262 Part 5. We really hope this gave you a clearer picture of the incredible effort and detail that goes into making our cars safer every day.